We will now talk about three very important properties of functions that they play key role in different applications. The first property is what we call injection, or a function being injective, or the other term for it, which is maybe more popular, is one-to-one. So we say this function is one-to-one. What does it mean for a function to be one-to-one? Function is one-to-one if you give it two different elements, it maps them to two different elements. Remember that a function cannot map one element to more than one element, but a function can map two elements to the same element. Again, if I have this set here, and I have this set B, nothing stops me from defining the functions like a function like this, right? So I map all three elements in A to the same element in B. However, this is not a one-to-one function. For the function to be one-to-one, I have to map every element to a different element in B, to a unique element in B. So the first thing you will notice that for a function to be one-to-one, I have to have at least the same number of elements in B as there are in A. Because if I want to map every element in A to a different element in B, I need sufficient numbers or sufficient elements in B for that to happen. So this is not one-to-one, but if I have this set A and this set B, and imagine I have four elements here, this is a one-to-one function. Notice that it mapped every element in A to a different element in B. So if we want to think about functions in general, giving an example of a function that's one-to-one, and imagine I'm talking about from the reals to the reals, so if from R to R, a function that's one-to-one, for example, is f of x equals x plus 1, okay? So this function does not map two different elements to the same element, right? So f of 2 is 3, f of 3 is 4. It's impossible to find two different real numbers, and then when you add 1 to them, all of a sudden they become the same, right? So this is one-to-one. But if you look at g of x, for example, equals x squared, now this is not one-to-one. Why is it not one-to-one? Because, for example, here are two elements that are mapped to the same element, right? So this function maps two elements to the same element. Therefore, this is not one-to-one, okay? So a one-to-one function maps every element in A to a unique element in B. I want to remind you once again that for that to be possible, the number of elements in B has to be at least the number of elements in A. So A, the size of A, has to be smaller than or equal to the size of B. Please keep this in mind, okay? So for a function to be injective, we map different elements in A to different elements in B. One implication of that if you are showing an injective function or a one-to-one function, that the size of A is at most the size of B. Okay. The second property is surjection, or a function being surjective or onto. This means that for every element in B, we have to have an element in A that maps to it. Once again, nothing in the definition of a function stops me from having this scenario. Right? So I can map. So this is a function f, but this is not onto. The reason for that is that there are elements in B that nothing mapped to them. In particular, this element and this element, nothing mapped to them. Therefore, this is not an onto function. So an onto function, we have to have a source for every element in B that is mapped to that. So if I want to show a function that is onto, and I have suppose here I have, let's say, 4 elements, and I want to have it being onto. Because I need to have a source for every element in B, I need at least 4 elements in A for the function to be onto. At least 4, because I cannot map one element in A to more than one element in B. That violates the definition of a function. So for me to be able to cover these 4 elements, I have to have at least 4 elements in A. Of course, I can have then more elements. So if I map this like this, this is an onto function, okay? This is an onto function. Let me actually draw this well here. This function g is onto, because if you look at every element in B, something in A map to it, okay? Now, again, we are not saying that exactly one element in A has to map to it. You can map multiple elements in A to an element in B. But this function is called onto, and again, if I go back to functions in general, like f from R to R, once again, f of x equal x plus 1 is onto. Every real number, you can find a number that you map to it, right? Because if you give me, for example, the number 5, f of 4 is 5. If you give me 500, f of 499 is 500. If you give me the square root of 2, f of the square root of 2 minus 1 is square root of 2. So this function is onto. However, once again, as we saw before, if you give me g of x squared, now this is not onto. Not onto. Why is that the case? Because for example, none of the negative numbers are gonna have anything mapped to them, right? So if I ask you, is there an x such that g of x equal minus 4? The answer is no. There's no such x, right? So this function g of x equal x squared is not an onto function. As we said, for one-to-one functions, the size of B has to be at least the size of A. If you have to have an onto, if the function has to be onto, we have to have sufficient elements in A to map to B. Therefore, if we have an onto function, if I have an onto function from A to B, then for sure the size of A is at least the size of B. Okay? Just think about it. If you have 4 elements in B and you want a function to be onto, you have to have at least 4 elements in A. Okay? So if we have a one-to-one function, the size of A is at most the size of B. If we have an onto function, the size of A is at least the size of B. Okay? Now, if we take these two properties together, combined, we have a bijection. So a bijection from A to B is a function that's one-to-one and onto. So again, the function f of x equal x plus 1 is a bijection because it's one-to-one and onto. F of x equal x squared is not a bijection. Not a bijection because it's neither one-to-one and neither one-to-one or onto. But keep in mind that for a function to be bijection, both of them have to be satisfied. For a function not to be a bijection, at least one of them is not satisfied. Okay, so a function that's one-to-one but not onto is not a bijection. A function that's onto but not one-to-one is not a bijection. A function that is neither onto nor one-to-one is not a bijection either. Okay? Now, notice something important here. Bijection has to be one-to-one and onto. Okay? So I said since f is one-to-one, we said this implies that the size of A is smaller than the size of B. Since f is onto, this implies that the size of A is greater than or equal to B. Since the function is one-to-one and onto, what does this imply? That the size of A is at most the size of B, and the size of A is at least the size of B. But how is this possible? Sorry about this. How is this possible that the size of A is at most the size of B and the size of A is at least the size of B? This is equivalent to saying that the size of A is the size of B. Okay? So if you have a function from A to B such that the function is one-to-one and onto, then you can already conclude that the sizes of these two sets are equal. And this is a very important and powerful tool when we are reasoning about sets. If I want to show that two sets have the same size, all I need to show, one way to do it, is by showing a bijection from A to B, or a bijection from B to A, it doesn't matter, okay? Again, usually with finite sets, that's not the problem. If we have two finite sets, we can count the elements in each of them and say, okay, well, this one has 500 elements, this one has 500 elements, therefore they have the same size. But when we go to infinite sets, things change completely there. So for example, we say that the integers and the natural numbers have the same cardinality, But how is that possible? Well, it's possible because we can come up with a bijection from z to n or from n to z. Okay? Again, this is not the subject of this lecture, but I want you to keep in mind that one powerful way of establishing that two sets have the same cardinality is by showing that there is a bijection from one to the other. In fact, when we go to infinite sets, that's the definition of what it means for two sets to have the same cardinality. It's by definition, we say that two infinite sets have the same cardinality if there is a bijection from one to the other.